How does noise combine with nonlinear dynamics? Amusingly, the simplest way to understand it is to understand how it combines with linear dynamics. And the linear case has a good pedigree. So linear flow plus white noise is something that was considered by Ornstein and Uhlenbeck a long time ago. And it's a harmonic oscillator of stochastic systems. So the linear flow that we have in mind is x dot times, in d dimension, a stability matrix, which is assumed constant proportional to x. And now if this stability matrix has only contracting eigenvalues, so all its eigenvalues or stability exponents are negative, this flow will contract to a fixed point at x equals 0. So x equals 0 is fixed point or equilibrium of this flow. Now what happens if you add noise to it? So we add a little bit of noise. Now to understand what the noise does, we have to describe what it does. And the simplest thing is to consider discrete evolution. So let's consider how does dx increment at time delta t. What does it look like if we knew what delta x was at 0? And we have evolved it for time t. We know that that's described by Jacobian. That goes for time delta t. And then we add noise to it. And these are all vectors in d dimensions. This is a matrix. And the noise we would like to be diffusive, which means that if we average over the noise, sigma I, sigma transpose j, we would like to be some kind of diffusion matrix, delta ij. And we want this to be dimensionally correct for diffusion, so the square of a quantity of the length diffuse is proportional to the time, so this should be defined as delta t times the diffusion constant. Diffusion matrix, the simplest case is one dimension, in which case that's a Brownian motion, and this is called 2 times d, or Einstein diffusion constant. So that's what we want to do with this. So now to find out how does the covariance move, covariance matrix is a matrix of delta x j transpose delta xi. So two-dimensional vectors averaged over many instances and configurations, and our intuition is that if I equals j, this is going to be a square of positive quantity, so this is going to be something, but there will be also off-diagonal elements. So this we define to be a covariance matrix of the distribution of deviations from the fixed point. And that depends on time, because these guys depend on time. They have always time. So we can do, this is a simple calculation. Put our formula here, and that's same as expectation value of the initial guy at time 0, I, L summed over indices, we go the time delta tau, delta t small time, forward in time, plus the noise accrued by that time, and then we multiply this by the transpose, which is j delta t Jm transposed. So, it should be really on the other side. Bear with me. Delta x 0. The whole thing transposed plus sigma I transposed. And now we expand this to the leading order delta tau. How do we do this? We know that for short time Jacobian is almost 1 because at 0 time nothing happens. And then it's plus the stability matrix A delta t. So that's what Jacobian looks like. Delta x of 0. Remember, Jacobian is e to the integral delta tau local matrix of velocity gradients at time t. So that's this guy here, and then we also get 1 plus delta time transpose of this thing, x transpose A transpose plus the noise transpose, and there is also plus the noise transpose, all averaged over many instances because we are looking at average over many Langevin and noisy trajectories, and that is equal to the first term just gives me delta x I at time 0, delta x j at times 0 averaged. From here I pick up another term which looks like this. So that is of course something to average, x transpose A transpose. And then I pick up the linear terming psi. They vanish because we assume that average drift is 0. And then we pick up this term here. So we pick up delta t Aj. And we realize these two terms are q at initial time. So we get a formula that says that the covariance Ij at time delta t minus this covariance Qij at original time, and everybody else is proportional to delta t, so we divide it. This delta t. This thing is proportional to the A. This is the covariance matrix at time 0 plus covariance matrix. It's a symmetric matrix, so transposes itself times A transpose plus delta, and that is also proportional to time. So this is obviously time derivative, so we get an equation that says the covariance matrix, d by t matrix, changes its time as something with the local shearing due to velocity gradients acting from the left, and that's now in the limit delta tau 0, this is the same time, plus q a transpose t plus delta. Now this equation has a very good pedigree. It was introduced by Lyapunov in 1892 in his PhD thesis in a study of stability of celestial mechanics. And it's lived long and productive life in control theory. So it's a central equation of the control theory. It's called Lyapunov and has nothing to do with Lyapunov exponents. It's a description of how covariance, so local noisy trajectories centered on deterministic trajectory up there. This would be a deterministic trajectory perturbed by noise. How that covariance develops in time, and it says that the change in covariance is proportional to the diffusion matrix, and it has to do with the dynamical stretching and shearing of the flow.